Hello everyone, welcome to Gate Academy. So here I am with the complete revision of the subject EMT. So because this is the end of the your preparation, the exam is going to come in few days. So this is the time where you are revising the subjects. So here is the solution for the complete revision of the subject EMT. So here it is completely for the electrical students, so that they can have the good command over the subjects in the last few days of the exam. So since it is having a very less weightage in your particular exam, but it is important because with the 3 to 4 marks you can get the good rank in the exam. So that's why it is important, and you cannot leave these subjects if you want to get the rank under 50. Okay, so let's talk about the weightage of the subject and how to prepare this subject. So after that we will revise it. So if I am talking about the electrical students, since I am talking about here about the electrical students, right? So for the electrical students, so this subject is having around 3 to 4 marks weightage, and generally 1 or 2 questions are asked. The both may be of 2 marks, so that's why it may contain the 4 marks maximum, and it may have the 1 question also, because in the last year, if you will see, only 1 question was asked. So in this particular subject you are having 2 chapters. In fact, we can write 3 chapters. One is coordinate system, second one is electrostatic, and third one is magnetostatic. So these are the 3 different chapters in this particular subject. So what you have to do is the weightage of the chapter is more in terms of electrostatic. If you will talk about the electrostatic chapter, so it is having the more weightage because the number of topic is more in this particular chapter. So if you have completed this subject and you are facing the problem in revision, then what you can do is you can follow this PDF. Okay, so here I have covered all the important points required to cover the whole subject, and the basic question if asked from this subject you can easily solve, and even if the bit complicated question is asked, then also you will be able to solve after looking this revision. Okay, so when you give the test, you will face you will see that the this type of this revision is very helpful for you now, because after this revision of this subject, when you appear in the test, in the mock test, like, so you will see the basic questions asked in this type of subjects. So that questions are important for your GATE exam as well. So that is why you cannot leave this subject, because you will see the difference what you were getting the before revision of this subject, and now after revision of this subject you will see the difference in 1 or 2 marks because of this subjects. Okay, so let's discuss this subject. So first is the coordinate system. So we will see the first chapter, which is a coordinate system and del operator. So in this chapter we have to talk about the different coordinate system, and these different coordinate systems are Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So these are the 3 basic coordinate system, and in each coordinate system we have to talk about the differential length, differential surface, and differential volume, and what are the different parameters available. Okay, so in Cartesian coordinate system the parameters are x, y, and z. So the coordinate system will look like this. This is the coordinate system. This is the coordinate system, Cartesian coordinate system, and here you can see that this is the origin, and when you move away from the origin you will find that the parameter x is increasing, okay, because you are moving in the positive x direction. And if you are increasing moving in the positive y direction, that means the y is increasing. and if you move in the upward direction, it means the z is increasing. What does it mean? So it means that the parameters are increasing, that means the unit vector will be in this direction of the parameter increasing. So if you will see the coordinate system, so this type of coordinate system is known as right hand coordinate system because it follows the right hand rule. And what is that right hand rule? So the right hand rule is that if you cross product ax and ay, then you will get the positive z. That means if you will curl your right hand from x to y, then the thumb will be pointing in the direction of z. So this is outside the board x and this is the y. So if you curl finger from outside to the direction of y, that is outside, and from the direction of y, if you will curl from x to, that is outside, and towards y, you will find that the thumb is pointing in upward direction. So thumb is pointing in upward direction, that means it is in the direction of z. So it is showing the direction of positive z axis. Similarly, if you will write ay cross az, then y to, this is the y, and y to z you have to curl your finger. Okay, so this is the y, and y to z you have to curl, and when you do y to z, you will see the thumb is pointing in the upward direction. So thumb is pointing in the outside the board, that means in x direction. Okay, so this is the right hand rule, and when you z cross x, when you will do the z cross x, you will find ay. So this is the z, and when you curl your right hand finger from z to x, x is outside the board, so z to x, then the thumb is pointing in the right hand direction, that is in the direction of y. So the y axis will be in this direction. So this is how we decide what would be the third coordinate. Okay, suppose this is x and this is y, then what will be the direction of z? So to find that this is x and this is y, so if you curl your finger from x to y, then thumb is pointing in the inside, thumb is pointing in the direction inside the board, that means the positive z axis will be inside the board. Okay, now you can also say that we have to write the coordinates in anti-clockwise direction. So this is x, then in anti-clockwise direction that will be y, and then it is z, and then again it is x. So this is the anti-clockwise direction. So in this way you have to consider the coordinates. This will be useful when you will consider the boundary condition, whether it is a electric field or magnetic field. So that will be useful to find the direction of electric field as well, because in this direction if the electric field is pointing, or if in this direction the flux is moving, then electric field is moving, then how to calculate the flux, which surface you have to calculate, all these things will be required. So that is why you have to first understand that how to consider the coordinates of any coordinate system. Okay, so this is all about the Cartesian coordinate system, basics of Cartesian coordinate system. Now the ranges of the coordinate system. So the range of coordinate system, all these parameters x, y and z are ranging from minus infinite to infinite. Okay, from this is origin, so 0 to positive, that is the plus infinity, from in the positive direction 0 to infinity, and similarly in the negative 0 to minus infinity, hence it is ranging from minus infinity to infinity, and all are showing the distance, hence they are ranging from minus infinite to infinite. Now you can see that this is the example of the plane. So examples are, first example is x equal to constant. So that is the constant plane, x is equal to constant, that means x can be anything, and the plane is nothing but y and z, because the two parameters are variable, x is constant. So in this direction, this is the direction of y, so y is changing and the z is also changing. So if this length is y and this length is z, then the area will be yz, or you can simply say this is a yz plane. And the second is y equal to constant. So suppose this is y is equal to 3, so you have to put the plane, this, suppose this is the plane, so you have to put the plane somewhere here, y at y equal to 3, because this is 0, so we have to put somewhere here. So in this direction, that is the outside, so this is the outside and this is the height, which is z. So this is z and this is x. So this is in the direction of x and this is in the direction of z. So the two parameter which is varying is x and z, and y is constant. That's why it is known as xz plane and y is equal to constant plane. Now z is equal to constant. Z is equal to constant. So z equal to constant we can see here. So z is equal to constant. Suppose z is equal to 3. Then z is equal to 3, it means it is placed in the positive direction somewhere here in some height. This is 0, so z equal to 3. If you want to place the plane z equal to suppose -2, so the plane would be somewhere here. This would be the plane. This is z axis. This is the plane at z equal to 2, somewhere here. So this is z equal to -2, this is z equal to 3. So here you can see that it is varying in this direction. So it is varying in this direction, that is in the direction of y, and it is in this direction, that is in parallel to the x. So that is why it is known as xy plane. So z equal to -2 or z equal to 3, that is known as xy plane. Now you can see the intersection of the planes x equal to 3 and y equal to -1 and z equal to 2 plane. So all these things, if you consider all the planes, so they are intersecting at this point. That's why this point is having the coordinate 3, -1 and 2, the intersection of all the planes. Now we have to see the differential length. So differential length of the Cartesian coordinate system is dx ax. So the distance in the direction of x is very small distance in the direction of x is dx, and the unit direction is in the direction of x. So this is the dx ax, dy ay and dz az. So we always take the differential length positive because we consider that the limit of integration will compensate the direction of differential length. Now the magnitude of differential length, that is, this is a vector quantity, so this is root over dx square, dy square and dz square, and differential volume is the product of all the three, dx, dy and dz. If you product it, you will get dx, dy and dz. And to find the differential surface, this is the differential surface. So to find the differential surface, what you have to do is you have to multiply the coefficient of 2 and in the direction of third. That means if you want to write the differential surface in the direction of z, that means it will be the multiplication of dx and dy. So dx, dy and az, the last one, what it shows is this is the surface which is having the normal in the direction of z, because the unit vector is az. That means it is showing that the direction is in the direction of z. And remember that we always take the direction of plane, that is normal to the surface and away from the surface, that means from inside to outside. Suppose you are considering the plane like this. This is the z axis and this is y and x. Okay, so suppose this is the plane z equal to 0. So if this is the plane, so the normal can be in this direction plus z and normal can be in this direction minus az, because this is the open surface. This is the surface like this, so it can have the normal in this direction and it can have the normal in this direction because both are open. So if we are talking about the open, that means it will be having the normal which is positive and negative. So this is positive and negative. Now suppose you are having the closed surface. Suppose you are having the closed surface like this, and in this case if I say write the direction of this, and suppose this is your y axis and suppose this is the z axis and this is the x axis, okay, and if you want to write the direction of this surface, this is also a plane, so if you want to write the direction of this surface, okay, so this is a closed object. Now how to write the direction? So what are the two parameters which is varying? First you have to find this. So the parameter which is varying is, this is the parameter which is varying in the direction of x, because this is outside, and this is the another parameter which is varying, which is normal, which is parallel to the z axis. So there are two parameters, that is dx and dz, which is varying. So the differential surface will be having dx and dz as area. Now what is the direction? Because the differential surface is a vector representation. See, vector representation of differential surface. So vector is having the direction. This is only about the magnitude. What would be the direction? So the direction would be normal to the surface, as I told you. So it is having the direction. So the direction, the magnitude we have calculated. So the direction is, this is the surface. So normal to the surface, this is the normal to the surface, and moving away from the object. So it is moving in the positive y direction. So this is ay cap. So this is the dx dy and ay cap. So this is the vector quantity, and which we have written here, dx dz ay, that is the surface which is having the normal in the positive y direction. Because it is having the normal in the positive y direction, that's why we have written ay. So what is the surface which will be having minus ay? So minus ay will be this surface. This will be the surface which is having normal in the minus y direction. Why? If you will see the direction here, it will be this side, because this is the free space. So inside to outside you have to move normal direction and from inside to outside. So that is the inside to outside, because this is the free space, this is the closed object. So this will be in the minus y direction, because this is the positive y axis. So the minus y axis will be in this direction. So this is minus ay. So now this is having the plus ay and minus ay direction. So with the alternative of this dx dz is y, we will be having here also the two parameter which is varying is nothing but the dx and dz. So the magnitude is same, dx and dz, but in the direction minus ay. So this is the differential surface, how we define the differential surface. So remember that the differential surface is having the direction normal to the surface, whatever plane you consider normal to the surface, and also the inside to outside, towards the open region you have to move to consider the direction of normal. Now we are having the third coordinate system. Circular coordinate system. Circular cylindrical coordinate system. So in this we have the three variables rho, phi and z, and they are having the range 0 to infinity, phi 0 to 2 pi, and z minus infinite to infinite. So this is the plane, xz plane, phi equal to 0 plane. This is the result of the unit vectors. And what is that rho, phi and z? Then the rho is nothing but the distance measured from the z axis. Rho is distance measured from the z axis, phi is the angle measured from the x axis, and z is the distance that is same as the Cartesian coordinate system. This is the rho equal to constant plane. So the outer surface of the cylinder will be considered as the rho is equal to constant surface, that is the circular area, or you can say if this is the bottle, so this is in shape of cylinder, so the surface of the bottle is having a constant radius. Okay, so this is nothing but the rho is equal to constant area or plane, rho equal to constant plane. Phi equal to constant plane. Phi equal to constant plane, that means in some particular angle if we are having a plane, so from the origin, that is from the z axis, it is changing, so this is the rho is changing and the height is also changing, that means z is changing. So what is constant is the value of phi. So phi is constant plane, which is a vertical plane perpendicular to the xy, making an angle phi with respect to xy plane. Okay. So this is the phi is equal to constant plane. Similarly, we will be having z equal to constant, which we consider already in case of Cartesian coordinate system. Now the differential length. So the differential length of the Cartesian coordinate cylindrical coordinate system is d rho a rho and rho d phi a phi and dz az, and the magnitude we can easily calculate because this is a vector quantity. So root over the d rho is square, rho d phi is square and dz is square. Differential volume is the product of all the three coefficients. So the coefficients are d rho d phi and dz. So product of these three is rho d phi dz, product of all these three. And when you want to write the differential surface, what you have to do is, if you want to write in the direction of unit vector az, then you have to multiply the other two coefficients. So when you multiply this rho d phi, you will get in the direction of z, that is in the direction of z, rho d phi. If you want to write in direction of a phi, then you have to take the product of the other two coefficients. So this is d rho and dz, so d rho and dz in the direction of phi. And if you want to write in the direction of a rho, then you have to product this rho d phi and dz. So this is rho d phi dz in the direction of a rho, that is this one. So whenever you want to write the differential surface, what you have to remember is differential length. And differential length, the direction you consider from the differential length and other two coefficients will be multiplied, not direction, only you have to take the coefficients. Now the spherical coordinate system, this is r, theta and phi. There are three parameters, and the ranges is 0 and to theta and 0 to pi and 0 to 2 pi. R is the radius of the sphere, theta is the angle measured from the z axis. You can see the angle measured from the z axis is theta, and phi is the angle measured from the x axis, and r is the radius of the sphere. So r is defined as the distance from the origin to point P. Theta is angle between the z axis and the position vector theta, a point P, and that is also known as azimuthal angle. R is equal to constant plane. R is equal to constant means the radius should be constant. So the radius is constant means the surface of the sphere. Now theta is equal to constant means at particular angle we have to move. This should be theta. So at particular angle you have to move, and in all the circular direction from 0 to 2 pi. This is phi equal to constant. The phi equal to constant means from here we have to move some particular angle, and then we can change other two parameters. So this is phi equal to constant. The relation between the Cartesian and spherical coordinates, if you want to change any point from the spherical to Cartesian and Cartesian to spherical. So suppose you are having a point and in which we are having r, theta and phi. This is the sequence of the coordinates in the spherical coordinate system. So r, theta and phi is given, and then we want to convert it into a point P in x, y and z. Okay. So r, theta and phi you can substitute here and you will get x, y and z. Similarly, if you want to change the P which is given in x, y and z, and you want to convert it into r, theta and phi, then you can use this relation. R is equal to root over x square plus y square plus z square, theta is equal to cos inverse z upon r, and phi is equal to tan inverse y by x. This is the diagram for the conversion. This is a cylindrical and Cartesian relationship. If you want to convert any vector from the cylindrical to Cartesian or Cartesian to cylinder, so if you want to calculate the Ax, then that is the coefficient of x component, then you have to multiply it by cos phi a rho minus sin phi a phi, and this is 0, and sin phi a rho and cos phi a phi and 0, and az in both the case same, because the z is having the same meaning in Cartesian coordinate system and cylindrical coordinate system. This is the relationship between the spherical and Cartesian coordinate system, which is same. If you want to calculate the coefficient of x, then you have to multiply the coefficient of r with sin theta cos phi, and theta cos phi, and phi component with minus sin phi. Now this is the next topic, which is the gradient of a scalar. We always calculate gradient of a scalar quantity. Gradient of a scalar is having both magnitude and direction. So this is the Cartesian coordinate system, del v upon del x ax, del v upon del y ay, and del v upon del z az. In Cartesian coordinate system, what you have to do is, whatever scalar product is given to you, scalar quantity is given to you, you have to differentiate with respect to x, with respect to y, and with respect to z, and multiply it with the direction of x and y and z, that is the unit vector in ax, ay, and az. And similarly for the cylindrical coordinate system, what you have to do is, this is the formula, and to remember this formula you have to remember the differential length. So differential length is d rho a rho and rho d phi a phi and dz az. So here we are having the rho term, so you have to multiply the rho in the denominator of the cylindrical coordinate system. The rest is same. The extra term is rho here, so divide that extra term here, you will get the gradient of scalar in cylindrical coordinate system. Okay, because here there is coefficient is 1, so this is 1, this is rho, and this is 1, and the product of the extra term is, here it is 1, here it is rho, here it is 1. The product of extra term is 1 into rho into 1, that is equal to rho. So the overall extra term is rho. Now similarly, if you write the differential length in case of a spherical coordinate system, if you write the differential length in case of a spherical coordinate system, then this differential length is dr ar and r d theta a theta and r sin theta d phi a phi. Okay. So in this case, the extra term is r here, and here r sin theta. So extra term associated with theta is r, so divide that r with theta. Rest is same. Rest what you have to do is, you just have to differentiate with respect to r, theta and phi, and multiply with the direction, that is the unit vector ar, a theta and a phi. What you have to remember is, you have to divide it by r, because in the differential length the extra term is r, and in the phi component the extra term is r sin theta, so you have to divide it by r sin theta. And product of all the three is 1 into r sin theta, that means overall extra term is r square sin theta. So you have to remember this, the product of all the three is r square sin theta in this cylindrical coordinate, spherical coordinate system. Now the divergence of a vector. So in Cartesian coordinate system, the divergence is nothing but because it is of a vector quantity, so the vector quantity is having x component, y component and z component. So differentiate the x component with respect to x, differentiate y component with respect to y, and differentiate z component with respect to z, and the result will be a scalar quantity. So gradient of a scalar is a vector quantity, but divergence of a vector is a scalar quantity. So the Cartesian coordinate system is this one, and the formula for in cylindrical coordinate system is this, and the spherical coordinate system, this is the formula. So this is the simple formula based question that you have to remember. And in the divergence we actually calculate the total outward flux at any point. So the divergence represents the net flux flowing at any point. It is a measure between the outflow and inflow. You can see that all the electric field lines, all the vector having field lines are outward, that means it is having a positive divergence, and here the incoming flux and outgoing flux are same, that means the incoming flux is even greater, okay, outgoing flux is greater than the incoming flux. You can see here the outgoing flux is greater and incoming flux is less. It means the field is diverging, that means for this the divergence will be positive. The divergence of a vector is positive if the net flow is outward. So the net flow is outward, so that's why the divergence is positive. The divergence of a vector is negative, so this is negative because it is having total inward field. So all the field lines at this point is inward, so that's why it is a negative divergence, and the field lines incoming and outgoing are same, then the divergence is 0. So a vector is said to be solenoidal, that is important. A vector is said to be solenoidal if its divergence is 0. Divergence is applicable only for a vector quantity, and the result of the divergence is always a scalar quantity. Now the curl. Curl gives the measure of the rotation of any field. So curl describes the rotation of a vector. It indicates the measure of tendency of a vector to rotate, vector quantity to rotate or twist or curl. It is a measure of how a field rotates about any point. So how to remember the formula for the Cartesian coordinate system? So this is nothing but the simply determinant of ax, ay, az, dx, del upon del x, del upon del y, del upon del z, and the x component, y component, and z component. The vector, we are having the curl of a vector, and the result is also a vector quantity because we are having the unit vector, because when we solve the differentiation determinant, you will get the vector quantity. Cylindrical coordinate system, what you have to do is, in case of differential length, what you are getting, the phi component is having an extra term, that is rho, so you have to multiply the rho with the phi component here also, and the product of all the three was rho. So you have to divide by rho, the determinant should be divided by that rho, the product of all the three. Similarly, in the spherical coordinate system, the product of all the three were r square sin theta, so you have to divide the determinant by r square sin theta, and the extra term associated with the theta was r, so you have to multiply the r here with the theta, and the extra term associated with phi was r sin theta, so here also r sin theta and r sin theta. Now the points you have to remember is, if the curl of any vector is 0, that means it is irrotational or conservative in nature. Here you can write it is conservative. Divergence of curl is always 0, so dc is equal to 0, that is, if you calculate the divergence of a curl, you will get the 0, because the curl of any vector we calculate, we will get the vector quantity, and this vector quantity can be calculated as the divergence of that vector quantity, but the result is always 0. Curl of gradient is also always equal to 0. When we calculate the gradient of a scalar, we get the vector quantity, and for that vector we can calculate the curl, but the result is always 0. The curl is always applicable for a vector quantity, and the result is always a vector quantity. Now this is the formula for a Laplacian coordinates, Laplacian of a scalar. So Laplacian of a scalar, this is the formula which is very less important. So you can remember this formula as well. Laplacian of a vector. How to calculate the Laplacian of a vector? So this is important because this is directly asked in GATE. This has been asked, and this is used in plane wave equation for the chapter plane wave equation. When you derive the plane wave equation, then this particular vector quantity will be used. Now we are having the chapter that is electrostatic. So electrostatic chapter will start from the Coulomb's law, and the Coulomb's law, which is simply nothing but a calculation of a force. If the 2 point charges are separated by some distance, then they will exert a force on each other. So here you can see that the force is given by the product of the two charges and inversely proportional to square of the distance. See here if you write the magnitude, the force is directly proportional to the product of two charges q1 and q2 and inversely proportional to the square of distance. So if we want to calculate the force from suppose the force exerted by q1 and q2 acts along the direction of r1 2, that means from 1 to 2, if you are finding the force on the charge 2 q2, that means you have to line join from 1 to 2. Suppose you want to calculate the force at this particular charge, then you have to join the line because of this charge. So when you will join the line in this direction, the force will act in this direction. So that is the direction of F12, and this is the product of these two charge. So this is the product of these two charge, directly proportional, and if we use the constant, so the constant is 1 upon 4 pi epsilon. So that is 1 upon 4 pi epsilon, and the distance between them, is the r12 vector and its magnitude. So this is the r12 vector, its magnitude, which is written here as r12, and the square of the distance, as we have written here, r square, so that is the square of distance, and the direction along the line joining. So direction of the force will be along the line joining between them. So if you are calculating the force on this charge because of this, then the line joining is in this direction. So that is why the force will be in this direction, and if they are opposite charges, positive and negative, then automatically the result will come negative and the direction of force will be changed. So always remember that whenever you are calculating the force, because of which charge you are calculating, line join from that charge to the point where you want to calculate the force, that is the final point. So we want to calculate the force at this point, so this will become our final point. This is our final point, and from because of this charge we are calculating, so simply do the line join from this particular charge to this particular final charge where we want to calculate the force. So this is a vector quantity, the vector unit vector. So the unit vector is equal to the vector divided by its magnitude. So if I want to write the vector in this direction, so what it would be, so a12 would be r12 vector divided by its magnitude, r12 magnitude. Okay, so this is r12 and r12 magnitude, and r12 magnitude is written as r12 here. So if you replace q1 q2 divided by 4 pi epsilon naught r12 square, and this is r12 vector divided by r12 again, then this would be q1 q2 upon 4 pi epsilon naught r12 vector divided by r12 whole cube. So that you are going to see in the next expression. Now what is the value of this epsilon naught? So the value of this epsilon naught is, the value of epsilon naught is 8.854 into 10 to the power minus 12, or you can also write 10 to the power minus 9 divided by 36 pi. r12 divided by its magnitude, and r12 is the displacement vector. The r12 is known as the displacement vector, which is the distance between the final point minus initial point. So we are calculating the force at this point. So r12 is the coordinate of this, that is r2 with respect to origin, and this is the position vector r1. So r12 is the 1 to 2 where we are calculating is our final point, and it is r12 is the displacement vector, which is written as final point minus initial point. So final point is having a position vector r2 and initial point is having a position vector r1. So the distance between the r2 and r1 is the displacement vector, and that is a vector quantity. So this is represented in the form of vector here. You can see r2 minus r1, so this will be a vector. Now the electric field intensity, it is nothing but the force per unit charge. So if you have calculated the force, you have to divide it by the particular charge. If you want to calculate the electric field at the point q2, then you have to divide by the charge q2. So the formula would be like this: Q upon 4 pi epsilon naught R square. Suppose here you want to calculate the electric field at this point, then because of this charge, so simply it is K Q by R square, where K is 1 upon 4 pi epsilon naught and the direction is in the direction of R. Again in the direction of R, that means where you want to calculate the electric field. If you are calculating the electric field at Q2, then means you have to join the line from Q1 to Q2, and that will be the direction of electric field and also the force. And the force is also given by Q into E. This force is Q into E. And here the charge we have considered is 1 coulomb, that's why it is written as F is equal to E here, because this is the unit charge. So the electric field is force per unit charge, and the unit of this electric field is volt per meter, or also the Newton per meter, force per Newton per coulomb. And if you will replace this unit vector in terms of a vector quantity, then it is vector r divided by its magnitude, so it will become r cube. So qr divided by 4 pi epsilon naught r cube. Electric flux density D is given by epsilon naught E, and flux is given by integration over the surface d dot ds. So these are important points. Now the continuous charge distribution, the line charge distribution, surface charge distribution and volume charge distribution. There are three types of charge distribution. The line charge, we have talked about the point charge, that is the point Q. So this is the point charge, but the charge may be distributed in the form of line, or in the line the charge may be distributed. So if the charge is distributed along the line, then it is represented as the line charge distribution and represented by line charge density, which is given as rho L. So line charge density is rho L, and if you want to calculate the charge over this part, charge in only this part of the line, so how can we calculate? So this is defined as the rho L. Rho L is having the unit coulomb per meter. That means if you multiply with the length, that means with the meter, then it will give you coulombs. So if you want to calculate the charge, over this length, that means you have to multiply the rho L with the particular length, that is dl. Hence it will be giving you the charge in that small part. Here you can see that this is the dq and rho L into dl. So what it shows is the charge in this particular small length. So if you want to calculate the charge over the complete length of the line, then what you have to do is you have to simply multiply, integrate over the length. Here you will see, if you want to calculate the total charge along the line, then you have to integrate over the length, which is rho L into dl. Now the surface charge density, it is also possible that the charge may be distributed over the surface, that is over the board. So the charge will be distributed like this, and if you want to calculate the surface, this is the suppose small surface, suppose this is the small surface, and here you want to calculate the charge. That means if this surface is denoted as ds, then you have to multiply the surface charge density rho s with the ds to calculate the charge in this particular part, okay. Now once you multiply, you will get the small charge, and after integrating over the surface, you will get the total charge. Similarly for the volume, if the charge is distributed along the volume, to get the charge you have to multiply the volume charge density rho v. The volume charge density is rho v with the volume dv, that is the small volume dv. So here you will see, to calculate the charge over this particular volume, we are multiplying the volume charge density with the dv, and to calculate the total charge, this complete charge, we are integrating over the volume. So after that we will get the total charge. This is the formula. Q is equal to integration over the V volume rho V dV. Now the electric field due to the various charge distribution, if there is an infinite line charge, the line charge is of infinite length and it is having the charge density rho L, then the formula is, this is the formula. This is the complete line charge which is placed along the z axis. This is the charge distribution completely along the length from minus infinite to infinite, and if we want to calculate the electric field at any point P which is having the perpendicular distance from the line to the point P is R. Okay. So in this particular case, the electric field intensity at point P is given by rho L upon 2 pi epsilon naught R and AR. That means AR is the unit vector in the direction perpendicular distance of point P from the line charge. That means line charge to point of interest. We are drawing the perpendicular line from the line charge to point of interest, and in this direction only the electric field is pointing. So the direction of electric field is also in the direction of perpendicular distance. Where you put the perpendicular line, that will be the direction of electric field if the line is of infinite long. Electric field due to the finite length of the wire, these are the formula. You can see it from the PDF. Electric field due to the circular ring. So if this is the circular ring and the charge, the line charge is, we are denoting the line charge, this is the line charge suppose, and we are forming this, by this line we are forming a circle. So whatever charge is present in this line charge, the same charge will be present in this circle also. So a simple line is converted into the form of a circle, and that is placed at z equal to 0 plane. So z equal to 0 means xy plane and center is origin. So in this particular case, the electric field in the normal direction and in the positive direction, because this is the charge, and from charge to the we are moving in the upward direction, that means in the positive z axis. So what will be the electric field? So here you can see that this electric field is rho L into R. R is the height, R is the radius of this circular loop, and the Z is the height, and 2 epsilon naught R square plus Z square whole to the power 3 by 2, and see, this is AZ. This is AZ because the ring, circular ring is placed in xy plane. So if it is placed in xy plane, so we are moving from the circle to the positive point. We are moving in the positive direction. Here this is the circle, and from we are moving in the positive direction to reach in the final point. We are moving in the positive z direction. That's why the electric field is pointing in the positive z direction. Suppose this point P is somewhere here. So in this particular case, we will be moving in the negative z direction, because this is our circular ring, and from this circular ring to reach to the point P, we are moving in the negative direction, that means minus AZ. So in that particular case, if you want to calculate the electric field at point Q, so that will be the rho L and R into Z upon 2 epsilon naught R square plus Z square. Everything will remain same, the magnitude will remain same, but the direction is now minus AZ. So at point Q, this will be the electric field, at point P, this is the electric field. So in this way we can calculate the electric field because of the circular ring. Electric field due to the circular disc. The disc is having some thickness, so the charge is distributed all along the disc like this. Complete disc is having a charge, and it is having the radius a. So if this is the surface distribution, the charge distribution over the surface or circular disc, then at this point P we are having the electric field, and again if this point P is in the positive direction, then the electric field intensity will be plus, and if the point P is in the negative direction, that is below this circular ring, then that will be in the negative direction. See what will be the formula. This is the formula: rho L upon 2 epsilon naught 1 minus h upon a square plus h square. A is the radius of this circular disc, h is the height where we want to calculate, this is the height where we want to calculate the electric field intensity, and this is Az because we are moving from the circular disc to the positive direction. If this point is below the circular disc, then it will be having a negative z direction. Electric field due to the infinite surface charge distribution. So electric field due to this infinite surface charge, that means if you extend this circular disc to the infinite line, if you extend the radius to the infinite extent, that means A is tending to infinity now. So if A is tending to infinity, this is 1 upon infinity becomes 0, so this whole term will become 0, and when this term becomes 0, this is rho s upon 2 epsilon naught. So we will get rho s upon 2 epsilon naught. Let's see. This is the formula: rho s upon 2 epsilon naught and An. An is the normal direction. Again, if you are moving in the positive direction, that means you have to take the unit vector positive, and you have to take the unit vector negative if you are moving in the negative direction, and that too in the normal direction. Direction normal to the surface. Okay. So suppose you are having a z plane. This is z equal to 0, this is the infinite extent, and at this point you want to calculate the electric field, which is z is equal to 5. So from z equal to 0 to z equal to 5, when you are moving, so you are moving in the positive z direction, that's why at this point P the electric field will be rho s upon 2 epsilon naught and plus Az, because you are moving from z equal to 0 to z equal to 5, and z equal to 5 is the point where you want to calculate the electric field. So here it is positive. Now suppose you want to calculate at z equal to minus 6. So it means you are moving from z equal to 0 to z equal to minus 6, that is a point Q. So here the electric field will be rho s upon 2 epsilon naught and direction will be minus Az. Direction would be minus Az because you are moving in the negative direction. So this is how we write the normal vector. Normal means, you know, that should be the normal to the surface. See here minus Az. Why? Because the point is below the xy plane. Now the Gauss law. What is that Gauss law? Gauss law states that the total electric flux passing through any closed surface. So the total flux passing through any closed surface is given by integration over the closed surface d dot ds is equal to total flux. This is the total flux passing through the closed surface. Here we can see integration over the closed surface d dot ds, and the total charge, that is equal to the charge enclosed by that closed surface. So this flux is equal to charge enclosed, and if the volume charge density is defined by rho v, then how do we calculate the total charge? To calculate the total charge, we integrate over the volume rho v dv. So this is the total charge, and this is also the charge, and according to the Gauss law the flux is also equal to the charge enclosed. So these two equations will be equal, and hence we get the Maxwell first equation, which is integration over the closed surface d dot ds is equal to integration over the volume rho v dv. Now the Maxwell first equation in the differential form, when you represent it by the divergence theorem, according to the divergence theorem, integration over the closed surface d dot ds is equal to integration over the volume divergence of d dv. So if we replace this as divergence of d dv, and this is also a volume integration, so this is rho v dv and this is del dot d dv, so these two will be equal, and hence we will get the Maxwell first equation in differential form and also known as point form. So divergence of d is equal to volume charge density, and for a source free region, if it is written as for a source free region, rho v is 0. So for a source free region, the divergence of d is equal to 0, that is known as solenoidal or the divergence less. Now electric field intensity due to a conducting sphere. So this is the conducting sphere. Conducting sphere is having the charge in the surface of the conductor. So this is the charge which is in the surface of the conductor. Now we want to calculate the electric field in three different cases. Point P, which is outside the conducting surface. So this is the conducting surface, and we want to calculate at any point P which is outside. That means the R is, the point of interest is greater than the radius. R is greater than A. So for this it is like a point charge, because the charge is having the surface is having a charge q, the total charge it is having is q. So at point P it is kq by r square simply. So you can see here, this is k 1 upon 4 pi epsilon naught q by r square in the direction of r. So at point P there is no change, it works as a simple point charge, and the total charge on the surface of the sphere is q, the total charge is q, and you can also calculate this charge by multiplying the surface charge density with the surface area of the sphere. So the surface area is 4 pi a square and the surface charge density is rho s, then this is equal to the total charge q, which you can write here. If it is given in the form of surface charge density of the conducting sphere, then you can calculate the rho s 4 pi a square, which is equal to q. Now if you want to calculate exactly on the surface of the sphere, so on the surface of the sphere the formula is same kq by r square, but exactly on the surface the point of interest and the radius are same, because we are calculating on the surface of the sphere. So the point of interest and the radius of the sphere are same, so this formula will be replaced by kq by a square. So you will see the same formula here. See, this is the same formula. K is nothing but 1 upon 4 pi epsilon naught and q upon a square. So q upon 4 pi epsilon naught a square. So this is the formula in the direction of r. Now the inside the conducting sphere, when you go inside the conducting sphere, because the charge is not present, and from the Gauss law we know that the total flux is equal to charge enclosed, and the charge enclosed is 0, so the flux is 0. So the flux is 0, that means integration d dot ds is 0, and hence d is 0, and d is equal to epsilon naught, E is equal to 0, it means E is 0. So the total electric field, because the charge inside the conducting sphere is 0, the electric field is 0. Here you can see d is equal to 0, E is equal to 0, d is equal to 0, E is equal to 0, because the Gaussian surface is not enclosing any charge. So this is the formula according to the result. For inside the sphere we are having 0 electric field, exactly on the surface we are having q upon 4 pi epsilon naught a square, which is a constant value, because surface is having a charge q and the radius a, that is a constant value. So at r less than it is 0, and exactly at a we are having the maximum value. And now as you are moving away from the sphere, the E is inversely proportional to r. E is inversely proportional to r square. It is inversely proportional to r square. So as you increase the value of r, the electric field is decreasing. Now electric field due to the non-conducting sphere. So suppose this is a non-conducting sphere. Non-conducting sphere is having the charge inside the sphere. So the charge is inside the sphere. Now if it is inside the sphere, so the point P is outside the sphere, so at output out of the sphere we are having the same electric field as that of the conducting sphere, that is kq by r square, and on the surface also we are having the same value. Here we have defined in terms of volume charge density. See, this is the same formula. The electric field intensity is given as kq by r square, right? At outside of the sphere it is kq by r square, but here we are calculating at the surface of the non-conducting sphere. So r is equal to a. So if I substitute r is equal to a here, I will get a square. Now this is the sphere, and sphere is having the charge on its volume because the charges are inside the sphere. So inside the sphere means it is having some volume. So the volume is rho v, or here it is written as rho v, and this is denoted as Coulomb per meter cube, and we have to multiply it with the volume of the non-conducting sphere, which is 4 by 3 pi a cube. So this is the total charge. Now when you substitute this charge, which is k 1 upon 4 pi epsilon naught and a square, and the total charge is rho v 4 by 3 pi a cube, then this 4 pi will get cancelled, this a cube a square and here it is cancelled. So we will get rho v into a divided by 3 epsilon naught, which we are getting rho v into a divided by 3 epsilon naught. So in this way we have got this result. So there is no extra calculation, or there is nothing change with respect to the conducting sphere. Okay, so this is the how we getting in the terms of rho v. So in case of non-conducting sphere, we are having the electric field at the outside of the sphere, which is same as the conducting sphere, which is kq by r square, and on the surface we have to equate the distance with equal to the radius of the sphere. So this case 1 and case 2 are same as the conducting sphere. Now the important point here is the third case, because in this particular case, third case, we are having the charge inside the sphere as well. Here we are having the charge. So if you are calculating inside the sphere, it means the sum portion of the charge will be enclosed. So here the sum portion will be enclosed, this portion will be enclosed, suppose. Here this is also the charges is present here also, because this is the radius a, okay, actual conductor, conducting sphere, non-conducting sphere. So how you are getting this result? Can you explain it? See, here are the charges, but the Gaussian surface is enclosing only this part which is inside this. So the total charge is distributed in 4 by 3 pi r, pi radius is a. So in this volume 4 by 3 pi a cube, the total charge is q. Okay. So in unit volume, in 1 unit volume, the total charge will be q upon 4 by 3 pi a cube. But we have to calculate the charge which is inside the Gaussian surface, and the Gaussian surface is having a radius r. This is r. Gaussian surface is having a radius r. So in the volume 4 by 3 pi r cube, the total charge is q upon 4 by 3 pi a cube multiplied with 4 by 3 pi r cube. So this 4 by 3 pi will get cancelled, and we get the q r cube divided by a cube. So this is the total charge which is enclosed by the Gaussian surface, q r cube by a cube, and the q is rho v into 4 by 3 and a cube, and this is r cube and divided by a cube. So this a cube will get cancelled. So maybe in this form it would be written, okay. So this is that the formula, and in the left hand side we are having d is into 4 pi r square, and which is equal to rho v 4 by 3, pi also will be there. So this is the total charge 4 pi by 3 r cube. Now this 4 pi and 4 pi will get cancelled, and this is also cancelled. So we will get rho v into r divided by 3 epsilon naught, because d is equal to epsilon naught E. So E is equal to rho v into r upon 3 epsilon naught. This we should get. See, rho v into r divided by 3 epsilon naught. Rho v into r upon 3 epsilon naught. So this is how you can calculate. So in case of non-conducting sphere, first you have to consider the overall charges distributed in which volume, and then the required volume. So this is nothing but the if you will see, it is the total charge is Q and desired volume divided by total volume. So ratio of the desired volume divided by total volume multiplied with the total charge is the total charge enclosed by this Gaussian surface. So this is the graph. Linearly it is varying. Here you can see that this electric field is proportional to the distance r. So up to the inside the sphere it will be linearly increasing. At r equal to a it is having some constant value, and after that it is decreasing because it is inversely proportional to r square. Now the potential difference between 2 points is given as the minus integration E dot dl. Potential due to the various charges, potential due to the line charge is given as 1 upon 4 pi epsilon naught integration rho l dl upon r. Potential due to the surface charge is given as 1 upon 4 pi epsilon naught integration over the surface rho s ds upon r, and potential due to the volume is k. This is 1 upon 4 pi epsilon naught, which is k, and the value of 1 upon 4 pi epsilon naught is 9 into 10 to the power 9. Okay, so 9 into 10 to the power 9 in integration over the volume rho v dv upon r. Discrete charges, if there are separate charges, then it is kq by r1, kq by r2, and add them together to get the total voltage. The potential due to the infinite long line charge is the line charge. If there is a line charge, then it is rho l upon 2 pi epsilon naught natural log of b upon a. This is the important result, that the potential Ra and Rb is the perpendicular distance. Potential difference and potential due to the conducting sphere. So this is the point, the potential due to the conducting sphere. Outside this, simply kq by r square is electric field intensity. Then when you integrate it, you will get this result, kq by r. Simply it will remain as a point charge, kq by r. Inside that, electric field is 0, so potential is 0. On the surface it is maximum, which is kq by r again. So outside and on the surface of the conducting sphere, the potential is same, and the relationship between the electric field intensity and potential is E is equal to minus of gradient of V. So electric field is a vector quantity, voltage is a scalar quantity. Integration over the closed loop, E dot dl is equal to 0. This is the Maxwell second equation. Total work done in a closed loop in presence of electric field is 0. See, here you can see, this implies that the no net work is done moving a point charge in a closed path in electrostatic field. This is referred as Maxwell's second equation in integral form. And when you apply the Stokes theorem, so curl of E equal to 0, that is the Maxwell second equation in point form. So these are the few formulas. Point charge, the potential is inversely proportional to R. In case of dipole, potential is inversely proportional to R square, and on the other hand electric field is inversely proportional to the r square in case of point charge, and in case of dipole it is inversely proportional to r cube. So the voltage is 1 power less with respect to electric field. It is r cube and r square, it is r square and r, 1 power is less. Energy density is given by energy stored in the electric field is 1 by 2 integration rho v dv, or you can write from here also. This is the actual formula. This is the 1 by 2 epsilon naught E dv. Actually it should be rho v dv only. This is the actual formula, right? 1 by 2 epsilon naught E square into volume, and volume charge density, if you want to calculate the volume charge density you have to divide it by volume. Energy density, so volume charge density, not energy, not volume charge density, it is energy density. So electrostatic energy density divided by volume, so you will get this. Now the capacitor. So parallel plate capacitor is epsilon naught A upon D. Isolated sphere is having a capacitance 4 pi epsilon naught A. Concentric sphere is having a capacitance 4 pi epsilon naught epsilon 1 upon A minus 1 upon B. And here the isolated sphere means B tends to infinity. Here the B tends to infinity. So if B tends to infinity, 1 upon infinity is 0. So this is 4 pi epsilon naught A. Concentric sphere. Now the coaxial cable is having a suppose length L, it is having a length L, so this is 2 pi epsilon naught L ln B by A. So you can change it, 2 pi epsilon naught L ln B by A. The length is missing. This is actually written in the form of, see, you can see here, this is written in the form of farad per meter. Okay, so if you write the capacitance 2 pi epsilon L upon ln outer radius divided by inner radius, so that will be in farad. Here it is written as the per unit length. So if you consider the length of the coaxial capacitor is L, then the formula is 2 pi epsilon naught L, which is the length of capacitor. Now the continuity equation, according to the continuity equation, this divergence of J is equal to minus del rho v upon del t, which is important for the matching of the two column. Relaxation time is epsilon upon sigma. Electric boundary condition, it shows that the tangential component of electric field in medium 1 is equal to the tangential component of electric field in medium 2, and normal component of electric flux density in medium 1 is equal to the normal component of electric flux density in medium 2. That is important. Tangential component in both the medium is same at the boundary. Whatever boundary is given, the tangential component is same of electric field, and the normal component of electric flux density is same when the rho s is 0, when the surface is having no charge. And if the surface is having a charge, then the difference between the flux density between the two medium is equal to the surface charge. Here it is written for the rho s equal to 0, or it would be dn1 minus dn2 is equal to rho s if rho s is present. Okay. Method of images. So if there is a perfectly conducting plane and above it if there is a charge configuration like the point charge, line charge, surface charge, volume charge, then it can be replaced as the image charge in the same height below the equipotential surface. So if this surface is having a v equal to 0, so whatever height you consider above the conducting plane, below the conducting plane there should be a image charge in the conducting region. Similarly for plus rho L it is minus rho L, plus minus rho V, and it is plus rho V. So image charges must be located in the conducting region. Image charges must be located such that the conducting region has the potential constant or 0, and if there is a point charge is placed, if there is a point charge placed between the two semi-infinite perfectly conducting, suppose this is a semi-infinite from 0 to infinity, and this is also a semi-infinite from 0 to infinity. Suppose this is x and this is y. There are two semi-infinite planes which are inclined at particular angle theta degree, suppose the angle between them is theta, then and the point charge is placed somewhere here, then in this case how many image charges will be present? So the image charges is 360 divided by theta, theta is in degree, minus 1, the number of image charges. Suppose it is placed like this, here it is the point charge q, so the image charge would be, here it is minus q and invert of it is plus q and the invert of it would be minus q. So if you will calculate this is the semi-infinite surface, so this is 90 degree, so 360 divided by 90 minus 1, which is 3. So the number of image charges are 3. Number of image charges are 3. So in this way we have to put the image charge, because we have to put the image charge in the conducting region. So the conducting regions are this one. So these are the conducting regions, and in this conducting region we have substituted the point charge, minus q, plus q and minus q, those are image charges. So this is all about the chapter electrostatic. Now we will move to the next chapter, magnetostatic. So next is magnetostatic. Magnetostatic chapter will start from the Biot-Savart's law, as the electrostatic starts from the Coulomb's law. So the Biot-Savart's law says that because of the current element, suppose if there is a conductor and it is having some small length dl, then this the current is flowing through this conductor. So the product, the current and the differential length, the small length, is known as the current element. So here you can see that the current element IDL, as shown in figure, this is the current element, actually this is the current element, and because of this current element, if you want to calculate the magnetic field at point P, then it is proportional to the product of the current element I, proportional to the current element IDL and the sine of angle between them. So the angle between the line joining and the conductor is theta, so sine of angle between them, and inversely proportional to the distance from the current element to the point P, the distance is r. Okay, so inversely proportional to square of distance between them. So when you write according to this, you will get the IDL cross AR divided by 4 pi r square. Actually it is DH. Okay, DH is equal to IDL, and it is proportional to the product IDL and proportional to the angle sin theta, and distance between them is r square. If you will write in terms of the unit vector, then this is IDL cross product with unit vector AR divided by r square. So it is written in this form, and the proportional constant is 1 upon 4 pi. Okay, we are revising the subject, right? So the few things you are knowing, that I am assuming, and if this is an infinite long current carrying conductor, suppose this is the infinite long straight current carrying conductor from minus infinite to infinite, and at any point P you want to calculate the magnetic field, so that is I upon 2 pi rho A phi cap. And also remember that the magnetic field, the direction of the magnetic field we calculate by right hand rule. That is, if the current is flowing in the conductor, so the right hand thumb is pointing in the direction of the current flowing through the conductor. So if the current flowing is in the upward direction, so the thumb should pointing in the upward direction, and finger encircling the conductor, will give you the direction of magnetic field, because magnetic field intensity is a vector quantity. So the direction we can calculate by right hand rule. So the direction of current is in the direction of thumb, and finger encircling the conductor will give you the direction of magnetic field. So that means this is the direction of magnetic field, because the current is flowing in this direction. The current is flowing in this direction. This is the conductor. See here, this is the conductor, and current is flowing in this direction. So if I encircle the fingers, so I am getting in this way. So this is the direction of magnetic field. So in this point P, the direction of magnetic field is inside. So here you can represent it by a cross, because when you encircle the finger, you can see that the finger is pointing inside the board. That means inside the board is represented by cross, and if the point of interest is somewhere here, suppose this is the point of interest, so in this particular case the finger is outside the board, so here you can represent it by dot. So the direction of magnetic field you can calculate in this way by right hand rule. So for an infinite long current carrying conductor, this is I upon 2 pi rho A phi, and which can also be used as, this is the A phi you can calculate mathematically as well. AL, that is the direction of flow of current cross A rho, perpendicular distance from the conductor to point of interest. This AL is the unit vector in the direction of current, and A rho or AR, this AR or A rho, if you write AR here, AR you can write, this AR is having the direction in the direction perpendicular to the conductor to point of interest. So whatever conductor is given to you, if you draw the perpendicular line to the point P in this direction, whatever will be the direction, suppose this is x-axis, so the direction of AR will be AX, and the direction of current, suppose the current is flowing in the y direction, so here the direction of current is AY. So AX cross AY, so the magnetic field will be in the direction of Z. In this way we can show. The direction of flow of current is AY, and this will be in fact minus AZ, right? Minus AZ, because inside the board we were getting, this is the direction of flow of current, and when we encircle this, if you are calculating the magnetic field at point P, so it will be represented here as cross, and cross means inside the board, and according to the coordinate system, this is y-axis, this is x-axis, and this is z-axis. So inside the board it is pointing, that's why we are getting the negative z. So this is AL cross AR actually give you the mathematical representation of the direction of magnetic field. So if you are not able to apply the right hand rule, then you can apply this AL cross AR. Remember that this AL or AI is the direction of current cross product with the direction of perpendicular distance. Always draw the perpendicular distance from conductor to point of interest. So this is the conductor and this is the point of interest. So you have to draw the perpendicular distance from conductor to point of interest. If you will do the opposite, the direction will be reverse, and this would be plus, which is wrong. Now the Amperes law states that the tangential component of magnetic field intensity around the closed loop is equal to the total current enclosed. This is integration over S dot dl I enclosed, and the current is also given by the conduction current density. You can see here the current enclosed is also given by conduction current density, and this is also current, this is also current, so these two are equal. So integration over H dot dl is equal to integration over the surface J dot ds will give you the Maxwell's third equation, which is derived from the Amperes law. So this is the Maxwell's third equation. Now in the form of a differential form or the point form, so curl of H is equal to J. This is for the static field, and for the time varying field there is one more extra term added with this curl of H. So the curl of H is also given by the conduction current density plus displacement current density. Okay, so this is sigma into E plus this is del D upon del T. Del D upon del T means the electric flux density with respect to the time, because this is for the time varying field, this is for the static field. Static field, that means that the field is not changing with respect to time. So applications of the Amperes law. because of the infinite long conductor, if you want to calculate the electric field, magnetic field at point P, then it is I upon 2 pi rho, simply A phi, as we have written just now. Here also we had written this I upon 2 pi rho A phi. This is also the same. And due to the coaxial cable, these are the formulas. Case 1, that means inside this, at this point somewhere here, and A to B, and then B to A, and these are the few formulas. That is not very much important. Let me derive it for you. I will derive it for you in short. See, if this is the first case, this is the radius A and this is the radius B, okay, and it is having some thickness. It is having some thickness. And it is having a radius C. Now, we are calculating this magnetic field at this point. At this point. At any distance r. Okay. The current flowing in the inner conductor is plus I and in the outer conductor is minus I. So according to the Amperes law says that integration over the closed loop H dot dl is equal to total current enclosed. So how much current this part is enclosing? This part is enclosing how much? We are drawing the Amperes path. So this is the closed loop. This is the Amperian path. This is Amperian path. Amperian path. Now the left hand side is h into 2 pi rho or 2 pi r, because we are calculating at r distance. Okay. Now the current enclosed is, how much current is enclosed? As we calculated in case of the charge, when it is enclosing, the desired volume divided by the total volume. Here the total current is I, which is flowing in the inner conductor, and the desired area, because this is the conductor and we are forming a closed loop, not surface, so it is a cross sectional area. So the desired area is pi r square and the total area is pi a square. So when you solve this pi and pi will get cancelled and you will get h is equal to, see, this is r and r will get cancelled, so we get I into r divided by 2 pi a square. So this is what we are getting here, I into r or rho you can write. Suppose we want to calculate at any distance rho, so this will become rho, so that is same. So how do we calculate? So we calculated it from the Amperes law, and Amperes law says that the integration over the closed loop H dot dl is equal to total current enclosed. So the shaded portion is actually the total current, but the total current flowing through this particular region is I, but the Amperian path is always only enclosing this part which is shaded. So this part is the desired area divided by total area. So this is how we have to calculate desired area divided by total area of the total current which is flowing, which is I, and h into 2 pi r in the left hand side, that will remain constant in all the case. Okay. So now let's calculate it for the other case. See here, between A to B. Now this is A, this is A and this is B. Okay, this is A and this is B. It is already written here, so let me not try it again. This is A and B. So now you want to calculate between A to B, that means in this region. In this region. So this is the Amperian path. Amperian path. Now the total current flowing from inside is I and in outer conductor is minus I. So the total current enclosed left hand side will remain same, h into 2 pi rho, and the total current enclosed is I. So you have to find the h. So this is I upon 2 pi rho. This is how you are getting I upon 2 pi rho. But when you calculate exactly on the surface, so this rho become A, which is written here. But actually it should be rho. It should not be A. It should be rho. So change it when you will take the printout of it. Then you change it, replace this A by rho, and I will also give you the new PDF for this. And in the case 3 is actually outside the in this region, where the minus I current is also flowing and the plus I current is also there. So the total area which is enclosed is, in the left hand side it is I h into 2 pi rho, and for the total current I is enclosed, and for the minus I, see 2 pi rho, the total current I is there, and minus I, how much part of minus I is actually enclosing. So the minus I is having the total area pi c square minus pi b square, and the desired area, this is the radius rho, so this is pi rho square minus pi b square. So when you solve this, I is common, we will get pi c square minus pi rho square divided by pi c square minus pi b square. So this pi and pi will get cancelled, and we are getting the same result here. What you are getting, see, this is minus sign. If you take minus rho square minus c square, rho square minus b square, in fact this should be the rho square minus c square, and in denominator we are having the c square minus b square. So in the numerator we can check once more. It is the desired area. So desired area is pi rho square minus pi b square. So pi rho square minus pi b square. So we will get this c square minus rho square only. So this should be this rho square. Here it should be c square. Now if we calculate the field here, if we calculate the magnetic field in the outside at this point P, so the total current is minus I and plus I. So the total current enclosed is I enclosed is plus I minus I, that means total current is 0. So the total current is 0, that means the field should be 0. Okay, so you can see here the outer conductor and inner conductor, this is, here you can see this is rho square minus b square only. It is c square minus rho square now. Okay, that was after, before solving it. The total current is the inner conductor current and the outer conductor current. Okay, that is okay. And outside that will be 0. Magnetic field due to the straight line. If the length is finite, we have considered for the infinite long. If the length is finite, then it is, you can see this is the angle which is with the upper point, and this is the angle which is with the lower point. So I upon 4 pi, this is the formula. B is equal to mu h, magnetic flux density. So I upon 4 pi rho sin alpha 2 minus sin alpha 1 a phi cap. Remember that alpha 2 is the angle with the upper end of the conductor. Upper end of the conductor is alpha 2 and lower end of the conductor alpha 1. If both the end of the conductor are above the point P, alpha 1 and alpha 2 are positive. If both the end of the conductor are below the point P, then alpha 2 and alpha 2 both are negative, and while if one end of the conductor is above P and other end of the conductor is below, then alpha 1 is negative and alpha 2 is positive, as shown in figure here. The lower end is given in the negative side, so alpha 1 will be negative, alpha 1 is negative and alpha 2 is positive. Magnetic field due to the circular conductor at the center is given as mu I upon 2 into R12. Magnetic flux density is given as B is equal to mu H, mu is equal to 4 pi into 10 to the power minus 7. This is the Maxwell fourth equation. Integration over the closed surface B dot ds is always equal to 0. The total flux passing through the closed surface is always equal to 0, and the divergence of B is equal to 0. That is the Maxwell fourth equation in differential form. Magnetic flux due to a solenoid. So if there is a solenoid, that means a long core and in which the wire is wounding, so the total magnetic field lying inside the solenoid is given by B is equal to mu naught Ni upon L, mu naught Ni upon L, and this N is also N by L. This is very important, mu naught Ni upon L. Remember that this formula you should remember, because it is integration B dot dl. See, this is H dot dl is equal to current enclosed, and which we can write is B dot dl is equal to mu naught into current enclosed, and it is B into the total length of the solenoid. The total length of the solenoid is small l. This is small l is the total length of the solenoid, so this is B into L, and mu naught and the total current enclosed, because there is a number of turns, so n number of turns and each turn is having a current I, so this is Ni, and you can write the B is equal to mu naught Ni upon L. So this would be the magnetic flux density. This is how you can remember the derivation, mu naught Ni upon L. Now this solenoid is converted into the form of a circular ring, then it becomes a toroid. So for the toroid, this is the formula, and this is also you can remember by the same B dot dl is equal to the current enclosed, and this can be written as B into, because this is in the form of circular, so the total length is its circumference, this is 2 pi r, and the current enclosed is, this is mu naught also, and the current enclosed is mu naught into number of turns into current. So now the formula for B is mu naught Ni divided by 2 pi r. If the we considering the non-magnetic core, if you consider the mu r, then you have to multiply it by mu r. So this is the formula you can see. These two formulas are same, mu naught Ni upon, from here you will get mu naught Ni upon 2 pi r, this is same. Magnetic field inside the toroid is not constant, it is the largest along the inner edge, while where the radius is small, because this is inversely proportional to the radius. Where the radius is less, the magnetic flux density will be more. So if the toroid is like this, in this region, if it is like this, then here at some point near the inner surface the magnetic field will be more, because the R will be less, and here the R will be more, and hence the magnetic field will be less. Now the magnetic scalar potential and vector potential, this is a scalar potential, H is equal to minus of gradient of magnetic vector potential. This is scalar magnetic potential. This magnetic field intensity is minus of gradient of magnetic scalar potential. Magnetic vector potential, so magnetic flux density is equal to the curl of magnetic vector potential. A is denoted as magnetic vector potential. Force due to the electric field is QE, force due to the magnetic field is QV cross B, and if we add these two forces, we will get the Lorentz force equation. So from here you can see that F is equal to QE, and force due to the magnetic field is QV cross B, and if we add them together, we will get Q times E plus V cross B. So this is the Lorentz force equation. Lorentz force equation. Now the magnetic boundary condition is also same as the electric boundary condition. We know that the tangential component of magnetic flux, magnetic field intensity is same. So the tangential component of magnetic field intensity in medium 1 is equal to the tangential component of magnetic field intensity in medium 2. So here you can see that the tangential component, if this surface charge density, surface current density is 0, HT1 is equal to HT2 if the current density K is 0. So if the interface is having 0 current, then the tangential component in medium 1 and tangential component in medium 2 of magnetic field intensity are same. And for magnetic flux density, the normal component in medium 1 and medium 2 are same. Here it is written in this form. The magnetic boundary condition is the normal component of magnetic flux density is equal to the normal component of magnetic flux density irrespective of the surface is having a current or not. So but in case of if the current is present, then what will happen? So if the current will be present on the surface, then the tangential component, difference of the tangential component of magnetic field intensity is equal to the current, or you can write in the form of the unit vector as well. So H1 minus H2 cross product with the normal unit vector from medium 1 to medium 2 is equal to the surface current density. So H1 minus H2 cross product with AN12 will give you the tangential component of magnetic field intensity. This is the diagram. If the field is coming from the medium 2 to medium 1 and it is making angle with the normal alpha 2 and alpha 1, then we can write tan alpha 1 divided by tan alpha 2 is equal to the relative permeability of medium 1 to permeability of medium 2. This is the medium 1 which is having a permeability mu r1 and this is mu r2. So the ratio of mu r1 and mu r2 will give you the ratio of tan alpha 1 to tan alpha 2. Now moving to the next topic, inductance. Inductance is directly proportional to the flux linkage with the number of turns divided by current. So the flux linkage N xi is defined as the product of the number of turns and the flux linkage each of them, and inductance, self inductance is defined as the ratio of the total flux linkage to the current. So N xi by I, where the xi is the flux. So this flux is given as integration over the closed surface B dot ds. So to represent or to calculate the inductance, we require to calculate the magnetic flux density, and magnetic flux density for solenoid you just calculated, that is mu naught n I upon the L, and here if you will substitute the value, you will get n into xi b into a, the b, this can be written as b into area. So b is mu naught n I upon L, so mu naught n I upon L into area, and this should be divided by current I. So this current and current will get cancelled and you will get mu naught n square A upon L. Mu naught n square A upon L would be the inductance for a solenoid. And these are for the some common configuration. If it is simple, the wire of the diameter 2a, this is the inductance, this is the hollow cylinder, this is for the parallel wire, this is for the coaxial, this is for the circular loop, and this is for the solenoid. As I calculated just now, mu naught n square a, S is the area, S is the area. S is the area. For torus in this type of structure, this table you can remember, especially this is very important for solenoid. Now the Faraday's law. A static field if there is a static magnetic field, there will be no flow of current through the circuit. But if there is a time varying magnetic field, then it will induce some EMF in the circuit, and for the induced EMF we will have some current. So a static magnetic field produces no current flow, but a time varying field produces the EMF in a closed circuit, which causes a flow of current. So this induced circuit is equal to the induced EMF. This induced EMF is equal to the time rate of change in the flux linkage. So this induced EMF is given by minus d lambda upon dt, where lambda is the flux linkage, and just now we defined the flux linkage is the number of turns multiplied with the flux through them. So n into xi. Now the xi is integration over the surface B dot ds. So integration over the surface B dot ds, this is all about the induced EMF, minus del n upon del t, where n is number of turns, and integration over the surface B dot ds. And we also know that the potential is defined as the integration E dot dl. So integration we get E dot dl, and these two are representing a EMF. So this is equation number 1 and 2, both are representing the same thing, which is the voltage. So these two are equal. So when we equate these two equations, integration E dot dl and minus del n upon del t B dot ds, and by Stokes theorem, if I change it to the curl, and this will be the Maxwell equation in integral form. This is the Maxwell equation in integral form, and when I apply the Stokes theorem, so this is the curl of E dot ds, so this is also ds, so this will be replaced to curl of E is equal to minus del B upon del T, and this is also the Maxwell third equation derived from the Faraday's law. So this is Maxwell equation, and this is also Maxwell equation, and if the number of turn is 1, so minus del B upon del T. So this is all about the Faraday's law. So why this minus sign is coming? So this minus sign shows that the direction of magnetic field, which is because of the original flow of current. Suppose if a conductor is having a current I, then because of that current I, the magnetic field will be generated. So the magnetic field will, because this magnetic field is time varying, so it will induce some EMF, and because of that induced EMF there will be a current flow through the circuit, and again there is a current which is known as the induced current, and this induced current will generate a induced magnetic field. So this induced magnetic field will be in such direction that will oppose the original magnetic field. So this negative sign shows that the induced magnetic field should be in the direction opposes to the direction of original magnetic field. So the direction of magnetic field opposes, induced magnetic field opposes the direction of original magnetic field, and this is given by the Lenge's law. So this negative sign has significance and it is defined by Lenge's law. So this is all about the subject EMT, and this subject, if you remember all these formula and the concept which I told you, then you will be able to solve the 1 or 2 question that is asked from this particular subject or this particular topic, magnetostatic and electrostatic. Thank you.